Do we have any quick question? Otherwise, we will move to the next talk. So the next talk is...
No, I have a question.
Oh, sorry. Yeah, I didn't notice you.
Sorry.
Please go ahead.
Over here. Recently, they've been trying to produce even more AI inference and training focused hardware, notably like the Google TPU or the Intel Habana, I believe it's called, chips. Would those be treated the same way as a GPU is?
I mean, absolutely. So, so GPUs, when we used to call GPUs like 6 years ago, it was exclusively NVIDIA GPUs. But now more and more technologies are coming up. Different vendors are coming up with accelerated technologies. Google TPUs is a little different, but those are also, accelerated technology. So yeah, those are all relevant.
So at some point, I think you talked about training on CPUs. So roughly, how many CPUs do you need to achieve the training performance, say the time cost of an equivalent of I don't know, is there a ratio or a thing that you have observed? Yeah.
Actually, it depends. So if you look at NVIDIA's numbers, those are always like, 450x or 1000x, it depends on the generation of CPUs, GPUs, but, GPUs have shown a tremendous performance for distributed training workloads. And I mean, there's a good reason, right? They have hardware which are capable of, executing things in a faster way. So like tensor cores. So if you're doing things in hardware versus doing things in software, so obviously there is bound to be a performance gain. But Arpan, do you have a number? Okay, Arpan is not here, but yeah.
I think the previous P100 Cascade Lake, and the performance is like very close. It's like 0.7%. So CPU can achieve good performance, but it depends on what you're comparing it to and the model that you're training, basically.
Thank you. So I'll have to move to the next talk. The title of the next talk is Benchmarking Parallel Python and Java Applications using OMB and MVAPICH2. And it's a joint talk by Dr. Aamir Shafi, who I just had the privilege to introduce, and Nawras Alnaasan, who is currently pursuing a PhD degree in computer science and engineering at The Ohio State University, working as a graduate research associate at the network-based computing laboratory. His research interests lie at the intersection of deep learning and high-performance computing. He's actively involved in several projects such as IDL, OMB, and Icicle. He's received his BS degree in computer science and engineering from The Ohio State University. So let's welcome our speakers.
Yes, thank you. So this next talk is going to be about benchmarking parallel Python and Java applications using OMB and MVAPICH2. So, my co-speaker is Nawras. So here is the agenda. First of all, we'll just have one slide on OMB, and then we have recently added new benchmarks to OMB that can be used for evaluating Java and Python communication performance. So I think a lot of the people here are already aware of OMB. So OMB is a benchmarking tool, that aids in measuring the performance of communication libraries on HPC systems with different configurations and hardware. There is already support for MPI, OpenSHMEM, UPC, UPC++. It provides a variety of benchmarks, point-to-point blocking, non-blocking collectives, and one-sided communication primitives. There is also support for NVIDIA and AMD GPUs. And today we'll be talking about Python and Java extensions to OMB. So basically these, we have recently made a release, so OMB 6.0, so you can, just go to the website, download this and give it a try. I would just like to say a word or two about the motivation here because, this is HPC community and when they hear about Java and Python, you might be thinking, why do we need this? But, we definitely need support for Python, deep learning requires it, machine learning, data science requires it. And for Java, we actually have a very practical use case that we are going to present in MUG. We are basically trying to support, Apache Spark over MPI. So Apache Spark is written in Scala and Java programming language. So essentially, it's a Java virtual machine based environment. So in order to utilize MPI from Apache Spark, we need some kind of, support for communication library that basically upper layer can utilize. So first I will talk about the Java extensions to OMB, but before I talk about the Java extensions, we have recently released a software that we call MVAPICH2J, which is a Java bindings to MVAPICH2. So OpenMPI, which is also another very popular MPI library, already has support for Java bindings. Okay, and historically before that, there were few, there was a project called MPI Java, there was another one called MPJ Express, Fast MPJ, all of these libraries were supporting, Java at the MPI level. But, when we started this project, the first question was, what API do we stick to? Because all of these different libraries have incompliant, APIs. So we just went ahead with the Java bindings API utilized by OpenMP so that at least MVAPICH2 and OpenMPI are compatible with one another. If we look at the figure at the right-hand side, so basically we are utilizing heavily on this package called Java Native Interface, which is part of Java Virtual Machine. And what this API allows you is that you can invoke native C functions from the Java level. So the goal here is that we don't want to re-implement any of the MPI functionality or any of the MPI communication at the Java layer because we know there is going to be performance overhead there. So we'd let MVAPICH2 optimize point-to-point collective communication, and we'll just simply use JNI to exploit all of those great functionality that MVAPICH2 or any other MPI library implements. So again, the use case that I was talking about, so I'll be talking again about this on Wednesday from 3 to 3:30. So, so this is a practical use case why we basically implemented MVAPICH2J. So this is now going into some details. So in C, it's pretty simple. We can just go do a malloc. We request memory. After that, it's not a typed language. C, we can convert this memory block into anything that we like or what the application requires. But Java is a type, it's a type-safe language. So it will, if you're going to work with arrays, you have to allocate arrays. If you're going to work with floats, you will allocate floats. And then the second challenge with Java is that it's basically, there's garbage collection. The memory management is done by the virtual machine. So you would allocate Java arrays, you would use it in your program, but you don't know when it get allocated, deallocated. And the Java virtual machine will run from time to time, and it will, move it from one place to the other, and all of that doesn't play well with, the kind of things that we do in HPC. So this is why there is something called direct byte buffers that you see on the right-hand side. So if you see the direct byte buffers, unlike Java arrays and indirect byte buffers, they do not reside in the heap memory of Java. So the actual memory is allocated in the C code outside, the Java virtual machine. But on the Java heap, you only have a pointer or a reference to that particular memory. And this memory is actually not subject to garbage collection. So if you're doing any MPI-based communication, you would obviously like to utilize these so-called direct byte buffers for doing the communication. So in MVAPICH2J, we have support for both communicating Java arrays as well as communicating direct byte buffers. And this is also true for OpenMPI Java bindings. Again, this is, I'm now going into a lot of details here. I'll skip this in the interest of time, but on the left-hand side, we are showing the use case, how Java arrays are being communicated. The right-hand side is showing, how byte buffers are being communicated. The only summary here is that although we have 4 steps on the left-hand side and 3 steps on the right-hand side. That 1, 2, 4 should be 1, 2, and 3. That's a typo. And one of the critical steps here is the extra step, which costs a lot on the left-hand side, is extra copy. So basically, whenever we are communicating Java arrays, we first copy those onto direct byte buffers before we pass a pointer down to the MVAPICH2 library. And that extra data copying is not present on the right-hand side path where users are utilizing direct byte buffers. So this is a summary of the Java extensions to OMB. So currently, I would call this an experimental sort of extensions. For point-to-point, we have support for OSU latency, bandwidth, by bandwidth. We have specific test cases for OpenMPI that we call OSU bandwidth OMPI and OSU by bandwidth OMPI. For collectives, we have support for all the blocking collectives, the widely used ones, and then we also have support for vectored collectives shown on the right-hand side. So here are some of the performance results that we have seen, and these are already published in IPDPS workshop this year. So the top results are intranode, the bottom ones are internode. And as you can see, we basically expect the direct byte buffer versions to perform better than the Java array versions, because obviously in the case of Java arrays, there is extra copy involved. And basically we see that, the buffer versions of MVAPICH2 and OpenMPI, they are performing better than the arrays version of MVAPICH2 and OpenMPI. We see similar trends for bandwidth, and as you can see on the right-hand side, top one. There is arrays. So for arrays, you're only able to exploit around, let's say, 20% of the bandwidth offered by the network. But for the buffer arrays, for the buffer API, both MVAPICH2 and OpenMPI, they can achieve for, let's say, messages like 128, 256K, they achieve, almost the maximum throughput possible. And then after that, for larger messages, the bandwidth usage essentially goes down. So similarly for collectives, the performance is highly dependent on the performance offered by the native MVAPICH2 library. But as far as the Java layer is concerned, the overhead is essentially minimal, as we have seen. So again, when we are comparing here MVAPICH2 and OpenMPI, so whoever wins, let's say, for those collectives in the native MVAPICH2 or OpenMPI library, we are seeing that the same kind of trend would be seen at the Java layer as well. So with this, I will now hand it over to my colleague Nawras for discussion on Python extension. Yes, please go ahead.
Can you go back to the Java binding? Yeah. Is this the one? Yes, yes, okay. But do you have any explanation why what exactly part of the Java binding is causing degradation for the overhead?
So which specifically are you looking at? So
yeah, is that because of the byte, coder or what? What part do you know? So if you know.
No, yeah, yes, absolutely. So so here we are talking about buffers, direct byte buffers, and then we are also talking about arrays. So for arrays, we know for sure what's the overhead. The overhead is the extra data copy, right? So when we are communicating Java arrays, this is a chunk of memory which is subject to garbage collection. So which means that I cannot register or pin this memory with the HCA, right? Let's say if I'm working on InfiniBand network, because this is garbage collection, the address will keep changing. I cannot pass this buffer, right? So basically for Java arrays, it's clear that's the overhead.
So that's basically so-called serialization before you actually send that message.
Exactly. So what we do is we take that data, we copy this to a direct byte buffer, and then we communicate. So for Java arrays, this one copy is the overhead. For direct byte buffers, the overhead is very minimal. If we compare MVAPICH2, let's say J using direct byte buffers and using, let's say, MVAPICH2, the overhead is quite minimal. Because direct byte buffers, the memory is, not subject to garbage collection. It's outside the Java virtual machine, and can be used for efficient communication.
Okay. Thank you.
Okay. Thank you, Aamir. So I will be talking about the Python extension to OMB. But before going into details, why Python? So as Arpan and Aamir in the previous talk, they talked about machine learning, deep learning, and data science. And to code applications in such domains, we need like frameworks such as TensorFlow, PyTorch, scikit-learn, and so on. And the main target language of these frameworks and libraries is Python. So Python has been gaining this rapidly growing popularity in the community. But one more thing, these ML, DL, and DS applications, they are considered very computationally intensive tasks. So we can really benefit from using HPC with Python. So to give an example here, let's imagine writing a deep learning application in C++. It will literally take thousands of lines and hours of debugging to like write a simple model and then train it on a data set. Whereas with Python, with a few lines of code, we can define our model, train it, and we're done. And that's basically like thanks to these frameworks we're talking about. So how can we use MPI with Python? As Aamir mentioned, the MPI standard, basically it provides bindings for the C and Fortran programming languages. So if you want to use MPI with a higher level programming language, such as Python, we need a wrapper library that provides MPI-like bindings. So MPI for Py is a widely used package for that purpose. And if we look at this diagram here, so at the lower level, we have the hardware, the HPC platforms, and then we have the message passing interface. It could be any implementation. And then above that, we have the languages that are calling MPI operations. So we can see that with Fortran and C, we can directly call MPI operations, whereas with Python, we need this wrapper library that we call MPI operations through. So for these reasons, we wanted to like find a way to evaluate the communication performance of MPI in Python. So we created this Python extension to the open source MPI suite. And in addition to that, we did performance evaluation of MPI communication in Python on different HPC systems. So we did point-to-point collective communication evaluation. We did that on the CPU and GPU with different buffers. And we also evaluated the pickle method, which we will talk about later. So basically, this table is a comparison between OMB for Python and the other benchmark packages.
So we can see here we have like point-to-point blocking collectives, vector variants, support for Python, and the different buffers for the CPU and the GPU. So if we look at this figure, it's the same figure from before. Where does OMB for Python fit? So here, if we look at here, OMB will measure the performance of MPI directly, whereas with OMB for Python, we're gonna build it on top of MPI for Py, so that it can measure the performance of MPI in Python. And these are the different benchmarks that are supported by OMB. So we have bidirectional bandwidth, bandwidth latency, multi-latency, different collectives, and vector variants. So this is the experimental setup. So I will show just a few samples of the evaluation that we done. If you're interested in the full paper, feel free to look it up. So yeah, we did the CPU evaluation on Frontera, Stampede, RA2. They all have different CPU architectures and node configurations. And the GPU evaluation, we did that on Bridges 2 with the V100 GPUs. So this is the point-to-point evaluation on the CPU. On the left, we have the small message sizes. To the right, the large message sizes. 3 different clusters, Frontera, Stampede 2, and RA2. And we can observe consistent trends across all 3 clusters. So we have this small overhead when we're doing MPI operations in Python compared to C. And it's around 0.4 microseconds for small message sizes. But for large message sizes, we can see that like the 2 curves are almost identical. And that's because relatively the overhead, even though it's larger than the smaller message sizes, but relatively it's very small that we can barely notice it. So this is the collective evaluation on CPU. We have all reduce and all gather. We can also notice the same trends as before. The average overhead is 0.9 microseconds for the small message sizes, and then it's around 14 to 23 microseconds for the large ones. And now this is the evaluation on the GPU. So in blue, we have the OMB numbers, basically the C numbers. And we have OMB for Python with 3 different buffers, CuPy, PyCUDA, and Numba. This is the point-to-point or reduce or gather. So we can see that for all these different benchmarks, the CuPy and PyCUDA buffers are doing better than Numba. And basically, we can still see the small overhead over the C MPI operations. So now this pickle method evaluation. So we are using a built-in feature with MPI for Py, which serializes the communicated objects. It's referred to as pickling. And we're converting the objects to byte streams and then unpickling them, converting them back to their original format when the receiver receives them. And these are the numbers. So green is the pickle method, orange is the buffer. For small message sizes, we see small overhead, but it's increasing as we are increasing the message size. And that's because there is this overhead of serializing objects. So if the message is bigger, the serialization overhead is also bigger. Okay. So to summarize, we presented the Java and Python extensions to OMB. Both Java and Python provides point-to-point and collective benchmarks. With Java, we're using MVAPICH2 and OpenMPI Java bindings. And for Python, we're using MPI for Py. With Python, we're doing evaluation, or the benchmark supports both CPU and GPU buffers. And finally, we recently released the Java and Python extensions with OMB, with the OMB6 release. So if you want to know more about them, please visit this link. And yes.
So for the Python extensions, is there any implementation needed to cope with the global interpreter lock in Python?
Can you explain more?
So let me take that. So this is all communication done in a single threaded environment. So the GIL is not coming into play here.
Okay.
So, you know, if you, with MPI, you're basically working with processes, right? You don't have a process which is multi-threaded. It's possible, but all this evaluation, there is just a process which has a single thread. So the GIL is not coming into a play here. You know, GIL will come into play if there is a process which has multiple threads in it, right? And all of them are doing communication. That is a possible scenario, but we have not done the evaluation yet.
Okay.
Yes.
Thanks.
I'm asking whether the Python stuff, is that a user interpretation mode, or have you ever tried for compilation?
Can you turn on the mic because I did not hear you?
With the Python test,
Yes.
was that user interpretation, or there is any compiled operations? I mean, whether you
Yeah.
generate the executable code.
Yeah. So like Python in general is an interpreted language, but the MPI4Py library, they use Python in their code. So there is the part that is compiled.
So the test itself actually is in the binary code you execute is still you see the pickle overhead.
No, the test itself is the benchmark written in Python, but in the back end, it uses MPI4Py, which is partly compiled.
Oh.
And
Can I see the evaluation part again, please? Evaluation part with the Python implementation. So even though it is a small gap, what is the main factor that it still have some kind of gap? Is it the innate from the Python to the C, or?
Yes. So, relating back to Donglai's question, yes, we are using Python, so we're translating Python objects to C objects so that MPI can understand them. So this translation is basically the causation for this overhead. And we have like in-depth analysis of the overhead in the paper if you're interested.
Okay. So which one is faster, Java or Python?
Python. If that's your question. So, I mean, if you see the overhead here, so this is zero, the latency here is 0.5 microseconds. So we are seeing higher, we are seeing higher latency with Java.
Okay, Python is
Are
good.
you happy with that answer?
Yes, I am.
That's good.
Yeah, thanks. Do you have time to go into any of the overhead and whether you think it could be reduced on the Python side for the small messages?
Have you heard the question?
It's okay. Can you please repeat the question?
You said that you have an analysis on the difference in overhead at 0.4 microseconds.
Do you wanna
Can
go
you
into
give
the
a quick
details
breakdown
of
on
the
where that's
overheads?
coming from and whether it can be
I think I
improved?
have this slide here.
So we have this slide, luckily. So do you want to explain this?
Yes. So here, this is like the analysis of what's happening exactly inside the send and receive MPI operation. And this is happening in the Python layer. So we can break down the send and receive operation into like 3 different phases. One of the phases, like this in blue, we are preparing the we are actually doing the receive operation. Orange is doing the send operation, and this green is like the extra conversion from Python to C. So we're converting we're basically preparing Python buffers so that they can be transmitted via C. Does that answer the
So basically it's the serialization, right? So if the memory exists in Python, we need to pass that pointer down to the C level. So sometimes for some data structures that's efficient, for others, they're not there yet. So it's the serialization is basically the overhead. But with Python, it's not, it's actually pretty minimal, right?
Yeah, so I'm not sure if it's called serialization, but the memory location in Python, we're translating it to a memory location in C, but we're just using different type of buffers. But with serialization, we're converting the whole object into a byte array, and then we're transmitting it.
Okay, thanks.
Just a moment. Yeah. Oh, we are on, right? The bar there, especially for 1 mega and half meg stuff, which part, I don't see the green jump too much particularly, because you can see the green. Green is the overhead, right? But it happened starting from what, 8K or 4K? All the way up. But suddenly we have the big latency.
That's right.
This is exactly what happened.
So just to clarify, these lines here, or columns, this is the overhead. So this is 0 to 8 is the overhead. But we have the blue is preparing the receive buffers, orange is preparing the send buffers, and then green is extra operations that are happening. So all of this, it's just showing overhead, breaking down where the overhead is coming from.
And this is for all reduce, and this is for all reduce operation.
Oh, the other one is percentage.
Yeah. So
Yeah.
this is going from 4 bytes going up to 1 megabyte, and this is for all reduce.
And here we're comparing the 3 different buffers, Kupai, Namba, and Bakuda. So this is happening on the GPU. It might seem a bit confusing, but with the context in the paper, it makes more sense.
Thank you. I think I get a gist of it. Yeah.
Yes.
If I look at this overhead analysis,
I think we need to wrap it up here.
Okay.
Sorry, but we're
okay, I can
already
ask after.
late. Yeah, maybe later. We can just take it offline. So thank you, both our speakers, Aamir and Nawras, for the great talk.